Let's discuss wallpaper groups. These are crystallographic groups, which are symmetries of patterns in two-dimensional Euclidean space, and therefore they are isometries of two-dimensional Euclidean space. The wallpaper groups, moreover, must have a lattice subgroup, which is two-dimensional. Isometries of two-dimensional Euclidean space, they come in four categories. They can be translations, like in the lattice of translations. They can be rotations. They can be reflections, or they can be glide reflections, as discussed in the context of frieze groups. So these are the possible isometries that can occur. Now, the possible lattices that can occur, the crystallographic lattices, are either oblique, rectangular, centered rectangular, square, or hexagonal. These are the 5 types of crystallographic lattices. The rotation groups that can occur, the so-called crystallographic rotations or angles, are rotations of order 2, 3, 4, or 6, or in other words, by 180 degrees, 120 degrees, 90 degrees, or 60 degrees. These are the possible crystallographic rotations. The classification of wallpaper groups becomes a matter of studying the possible lattices and then the possible extra discrete symmetries, like reflections and rotations that are compatible with those lattices. We won't do the full classification, but we'll study a few examples that illustrate the complete classification. The first case is very clear. We have an oblique lattice, so some parallelogram, and then we have some random image inside it, and then we copy this random image in each fundamental cell. And because it doesn't have any extra symmetry, basically the wallpaper group is just a two-dimensional lattice, lambda 2, which is the wallpaper group, and this wallpaper group is called P1. The second example is where we have again this cell, but now we use the symmetry of this fundamental cell to add some symmetry to the pattern. So a symmetry is the point reflection with respect to this point, or a rotation of 180 degrees. So a rotation of order 2, and this pattern will be called, therefore, P2. So what is it? Well, we draw some picture on this side, and then we must draw the analogous picture on the other side. And then this pattern, when repeated over all of the parallelograms, is now a pattern with symmetry P2 with a Z2 point group. A fundamental cell for this case is if we just cut the parallelogram into 2, then we get a fundamental cell. These are the 2 cases for a generic lattice. But if we have a more specific lattice, we get many more cases. Let's look at a second fundamental cell, now of the form of a rectangle. So if we have a rectangle, we get some more symmetry axes that we can use to make our pattern more complicated, more symmetric. Like we have this symmetry axis, this symmetry axis. So for instance, we can invent a pattern which is of the type where we reflect along a horizontal axis. So let's just draw a pattern here and then just reflect it. This will generate its own wallpaper group. Another example is where instead of a reflection, we do a glide reflection along this axis. So if we take this pattern, but then glide reflect it, we also have a new wallpaper group. This one contains a reflection, this one, or a mirroring, and this one contains a glide reflection. For the rectangular lattice case, we'll get 5 more patterns. So we go from 3 all the way up to 7. If we have a centered rectangular lattice, then we get some more possibilities, because now we have a point in the middle, and so we can do, for instance, a glide reflection along one of these axes to match one of the points on the edge. So an interesting pattern here that is new compared to the previous ones is where we do such a glide reflection. So we put some pattern here, but then we glide reflect it. Well, we reflect it first of all, but we also glide reflect it all the way here and here. If one does this accurately, one gets a new pattern. So the centered rectangular lattices add another 2 patterns to our list. And then the square lattice, of course, has lots of symmetries and adds another 3 to our list of patterns. So 10, 11, 12. Now the final list of lattices from 13 to 17, or the final list of wallpaper groups, has to do with the hexagonal lattice. So let's draw a hexagonal lattice, and let's draw a nice new pattern, one of the 5. So we can have this lattice, we can have this symmetry axis, we can have this symmetry axis, and we can have this symmetry axis. This point is in the middle. And then around this point, we can do a rotation of 60 degrees to repeat a given pattern, like this, and so on. This, for instance, has the name P6 for a order 6 rotational symmetry. And then we have another reflection, which is indicated by an M. So this wallpaper group, which is the symmetry of this pattern, is P6M. There are 3 such patterns with symmetry groups of order 3, with rotation groups of order 3, and 2 with rotation groups of order 6, for a total of 5, for a total of, in the end, 17 distinct wallpaper groups. The point groups of these wallpaper groups are basically Z2s, or Z2 times Z2, or dihedral groups of order 3, 4, or 6. Now, if you want to make your own wallpaper, what would you do? Well, you would first identify a fundamental domain. This will have a particular shape. Like in the example we just saw, a fundamental domain would be one of these triangles here. This would be one fundamental domain. And then use the symmetry operations to copy the fundamental domain. The image within the fundamental domain should have no extra symmetry. You can do this for all 17 wallpaper groups and make your own very distinct list of 17 wallpapers.